Hi, I'm Bill Adams with Lightwave Technologies. We manufacture the Edge, which is our topographic and bathymetric LiDAR system for shallow water mapping. We're here in Peoria, Arizona with Extreme Aerial Productions doing a survey of the technology here at a lake behind us here. So this is the Edge, and I'm going to go through how the hardware works. So what we'll do is we'll mount it to the M600 here. The mounting mechanism just clips on right to the bottom. It's fully autonomous from the drone. So there's no need to mount any cables, do any wiring. It's completely independent from the software. So there's nothing that you need to do to integrate it onto any platform. It's a 5-kilogram payload, so it can fly on any UAV that can carry 5 kilograms or more. So what we have here is our mounting hardware. We have our GPS antennas for the IMU. These arms will actually extend out further, so to get away from the drone body, just so we get better heading, because again, we're not relying on the drone systems for anything. It's only carrying the payload. So we have our USB interface here. All the data is stored and written here on this USB drive. Removable battery container here, so you can just swap the batteries out here. Battery goes in right there. It's your standard lithium-ion battery, and you get about an hour of operation time with this battery. So how it works, there's only 3 buttons on the entire system. There's a power button, a start button, and a stop button. What you're going to be looking for are certain indicators to know when the system is ready. So how the workflow works is once you've mounted on to the UAV, you'll push the power button to power the system on. What'll happen is it's going to look for the USB to make sure that there's something to write the data to, and this USB indicator light will turn green. The next thing that it's going to do is look for its GPS. So that's what these antennas are for. This can take anywhere from a minute to 5 minutes, depending on where you are, whether you're in a remote location or a more urban environment. So once your GPS is locked, that light will turn green. These top 3 lights will all turn green, and your system ready light here will tell you that you're ready to start flying. So from there, you'll push and hold the start button for about a second. The save icon will start flashing, meaning it's starting to write data. And when your laser is firing, your laser firing will be flashing red here. You'll be able to see the laser on the helicopter pad, so you'll know it's firing there. From there, you're ready to take off, go and collect your flight. When you're done collecting your data there, you'll just press and hold the stop button. Depending on how big of a flight you'll do, it'll take anywhere from 15 seconds to a minute to write all the data on, which is why this save icon will be flashing green. That means it's writing data to the USB stick. Once that is done, these top 3 lights I mentioned earlier will be green. From there, you can either power down the system to take the USB out, or you can just push start and go do another flight. So that's the standard workflow for the hardware operation of the Edge sensor. So another thing to understand with this sensor is it is a very conditional sensor. Your turbidity, meaning your water clarity, is going to be one of the biggest limiting factors of the sensor. It's light, we can't trick physics. If you have a lot of suspended particulate in the water or a really dark bottom surface, that can affect how deep you can see. So it's always really important to test the quality of the water that you had. I've already gone and collected a couple samples down here, and what comes with the unit is a nephelometer. So this is just a standard turbidity meter. It's always, always crucial, unless you know your site water is good, to understand what turbidity you're dealing with. You'll never want to fly after a storm where a lot of runoff comes in and increases your turbidity. So how this works is I'm just going to take a sample here, pour it into the test vial there. Stick this down here. You want to make sure it's really clean and you don't have any dirt on the outside, because that can affect your reading. And what we have for this is a calibration. So this will also come with it, so we know that this water is 0 NTU, so you can use it to calibrate your nephelometer just to make sure it's reading the right measurements. So you put it in here, close that, we'll power it on, and then we'll hold. As soon as it wants to, run test. 0, 0. So that's good. So we know it's calibrated. So we're gonna run this. I'm just gonna give it a look, make sure there's no dirt on it. We'll want anything less than 5 NTU to be able to hit the bottom is what we're looking for. So the lower that number is, so we have a 3.4 NTU, so that's good. So that'll be really helpful for the data that we're about to collect here, so that's good to know. But I have multiple samples. We'll just want to test the other one too, because I took this next one at a deeper spot. So you'll get 2 vials with it. Yeah, so your bottom surface will come into play. When you have a dark black bottom, that'll affect your point density versus a sandy, silty, rocky bottom, which is reflective. That helps. So we're gonna run the next test here. 4.8, okay. So that was a more near shore one. So that means that's kind of what you would expect when you have a lot of vegetation near the shore that kind of piles up and can suspend a little more versus things that have a chance to settle out in the deeper part. So that lines up, but these are pretty decent NTUs. So we should be hitting anywhere from 7 to 10 meter depths given the bottom surfaces. So that should be good. When I was down there, you could see pretty far out. You could see structures in the water, so that'll be good. So if you look here, when we plug in the antennas, you'll see a little red circle indicator. So that means that you'll plug this antenna to that red circle. But what it also means is when you're mounting it, you want those red circles on the back. So the control panel will always facing out to the right of the body. So it'll be coming, we'll mount it just in here off the front. Put one side in. So we'll just pull that all the way out here. There's a little pin there where you know that you've hit the right point. Tighten that up, make sure those are pointing up. So the next thing we're gonna do is we're gonna power on the unit for the GPS to lock. This, as I said earlier, this could take anywhere from 1 minute to 5 minutes. So we're gonna go ahead and hold the power button. System's now powering on. All right, we found the USB. Now we're waiting for the GPS to lock. So we'll just let it sit there until that green light turns on. When that third green light turns on, then we're ready to start the unit and do our first flights. All right, so we have the sensor fully mounted onto the M600. Our GPS is locked, our USB is red, so we're gonna go ahead and start the system and do our first flight. So I'm gonna press and hold the start button. Got our laser flashing, we got our saving going. All right, saving's writing. All right, laser is firing, we are ready to take off. All right, so we've taken the USB stick out of the sensor and are looking at our first batch of data. So every time you push the start button, it's going to generate 3 files. It's gonna be your edge bin file, which is your point cloud, your IMU post, which is your IMU data, and your camera file from the camera that's on the bottom of the sensor. So every time you push the start button, 3 of these files are generated. You'll see that they're time-stamped with today's date, and you'll be able to tell which flight number it is with the last 3 digits on the end of the file name. So you'll see that this first flight is 000. The next time we do it, it'll be 001. After that, 002. So that way you'll be able to keep track of which files correspond to which flights. And right here I have ParseEdge, which is our in-house LiDAR processing software. So this is how we do what's called our quick view step. So when we're out in the field like today, you take the USB stick out and look at your data. You'll be able to assess your overlap, if you're hitting your targets. Are you getting Bathy data? Are you not? Do you need to change something? So you don't have to go back to the office and process there and realize you need to come back out. So how this works is we'll select our input file. So I'm gonna select file and navigate to where I dropped those files. And what we're gonna use is our bin file, our edge bin file. So I'm gonna open that in the software. We're gonna change our output location, so where you want the process file to go. I'm gonna go ahead and put it in that same folder. We're gonna hit save. All right, so once you have your input file selected and your output location, you're just gonna click process. You'll be able to see it working here from the GUI window, so you'll be able to see how far it is to complete. So we'll just let that run for a second. Shouldn't take very long at all. File successfully created. Perfect. Okay, so we just finished running our quick view program So that generates two files when you complete the processing for the quick view. Your UTM file, which is your point cloud, and your Astrolite DAT file, which you'll use in a later step for the classification piece of the post-processing. So what we're gonna do is we're gonna minimize this window. We're gonna take that UTM file and load it into our visualizer, which is Cloud Compare in this case. It's looking at all our scalar fields. We will apply, well, yes. It's generating the number of points. And here we have a rough view of our point cloud from our test flight. So what I'm gonna do, I'm gonna turn on the IDO lighting. I'm gonna click the file here. We're gonna make these points a little bigger, just so we can see them. Let's make them a 3. So you'll see, this was our takeoff spot. We did a little rotation here around over the berm here, which you're seeing here. You're seeing the tip of some of those trees right there. Taking it around here, didn't quite get any water in this flight here, but we're getting bushes, trees, the system's working great, so that's what we want. Oh, let me click that again. So we can color this by height. Well, this will be our polarization, so for the polarization view, this will be very critical for the bathy piece. So when it's topography, the red and blue points will be together. When you're getting bathy, they'll separate. So that's how we'll know we'll have bathy, where the red will be the water surface and the blue will be the underneath the water surface. So the polarization is what you're going to be using to make sure that you have bathy in your quick view data sets. But you can see this data set doesn't have very much GPS drift, which is really good. Sometimes when you do longer flights, you'll see different elevations between these flight lines, or maybe something gets a little wonky. That's usually GPS drift. You'll also see that we have some noise here, just on the bottom underneath there. So you'll get a rough point cloud. It's not going to be GPS corrected, but you'll be able to see if you're hitting your targets, you have the right overlap, and you're getting bathymetric data, which is what this is for. So from this data set, we can say that the system is good to go. So we're ready to continue the flights for the day.